Assimilation parameter solving.
Yes,
Elizabeth.
thank you for having me today. So as she mentioned, I will be focusing on data assimilation and parameter recovery in particular. There's a bunch of other things at the very end of the talk that we may or may not get to, but I also keep this kind of informal and more like introductory level. So we're going to start with kind of a background. What is data assimilation? We're going to talk about this novel data assimilation algorithm that came out in 2014. We're going to look at some theoretical and applied investigations, specifically in the area of parameter recovery. And we may talk about some sensitivity and some applications to ocean models and maybe a little bit of current feature work. But we're mostly going to focus on parameter error and recovery. So the idea here is we want to, the point of looking at, for example, the Navier-Stokes equations, of course, is to model the real world, right? We want to model ocean flow or air flow or some sort of fluid flow. So we want to model these physical phenomena like the oceans or the atmosphere. And in these specific situations, we have a lot of observations, but there's no initial data, right? If I'm given a PDE, I usually generally am looking at some sort of initial value problem. That's kind of the setting I'm considering here. So if we've got, say, a field, we would have to measure everywhere in space in order to accurately initialize the PDE, which is pretty much infeasible. So the problem is if we don't have this good initial condition with chaotic systems, we're not going to necessarily, we're going to kind of like diverge, or our solution is going to diverge from the true solution that we want. So instead, the idea behind data assimilation is to incorporate observational measurements into the model in order to basically force the model to match up to the true solution of what's actually happening in, say, the weather field or the lake or the ocean or something like this. In the applied fields, generally they use statistical methods like Kalman filter and 4D var. We could get into a discussion on that. We may, if anybody has some questions on that. But specifically, we're going to focus on a continuous version today, something that's much more tractable analytically. The idea is that data assimilation addresses this near impossibility of obtaining correct initial conditions and is also used to help sometimes minimize error from incorrect model physics by using the data to adaptively correct the model. And we're going to talk a little bit about this in the context of recovering parameters, specifically viscosity in the Navier-Stokes equations. And then we'll go into Lorenz and we'll talk about recovering the three mean parameters in there as well. So specifically, let's start with the data assimilation technique. So if I'm looking at, let U be the solution to this distributive dynamical system, du dt equals f of u, where think of, this is just Newton's second law, so just think of f of u as the right-hand side of the Navier-Stokes equations. And then I don't have any known initial data, but I know how the physics should be evolving. So I'm going to say that I'm observing, so if I have like a field and I am observing, I have like observation stations spaced h kilometers apart. So h would be like the spatial discretization in some sense, if you think about it like that. So I'm observing on a grid, say some nice uniformly spaced grid over an entire domain. So I'm going to observe these and I'm going to interpolate them. I'm going to interpolate the observations, say linearly or something like this in a physical sense. So if I observe one here and two here in like meters per second, I'll interpolate in between and say the velocity should be approximately between, should be the line x plus 1, right? If you're starting at 0, something like that. So I'm going to take those observations, I'm going to interpolate them in space, and that'll give me this IH of u operator. So IH of u we know. So we're going to construct this system, which evolves dynamically the same way, plus we have this feedback control term. And then we're going to initialize with whatever, anything that's sufficiently regular. So generally in a lot of our simulations, we'll just use 0. So it doesn't matter where we start now, because this term, and I'll describe what it does here, is going to drive us towards the true solution, agnostic to this initial condition. So what's happening in this term here? It's a feedback control term. So basically, if I have dv dt equals f of v, whatever the physics is, minus this operator, if I'm looking at v being the solution, just bear with that for a second, of this equation, then I can look at v at the points that I'm observing u in the physical field, right? So I can also interpolate v on that discrete grid. So if I want to look at that, here's in 1D, a 1D like caricature. So here's my IH of u. So I'm observing, I know these points for a fact, these blue points for a fact. And I'm going to interpolate them linearly. And then I'm going to observe v, whatever the solution to this guy is, at those exact same points. And I'm also going to interpolate it linearly. So I don't know U, but I know IH of U. I know V and IH of V, supposing I can solve this guy. Now, what's happening here is I have IH of V minus IH of U. If I look at these points, what's happening here is think discretely at time Tn, I'm going to have something for V, and then at time Tn plus 1, I'm going to evolve it with the dynamics, but I'm also going to look at the difference, basically the error between IH of U and IH of V. And I'm going to say if IH of V is above IH of U, I want to drive it down, right? So I basically want to look at the error. So this error would be positive. So I want to drive the change in the system towards IH of U. So I'm going to do that, and I'm going to do it, I'm going to kick it really hard. This mu is called the positive relaxation parameter. In a lot of statistical methods, mu is generalized to be some sort of, it's often like a common gain matrix, for example, but that specifically works analytically in linear systems, which are not what we're concerned about. We want these nonlinear systems. We want to look at those analytically. Another advantage of this approach with this feedback control term is that it doesn't implement a lot of the mess that these other statistical methods work with. It's a good mess, but it's very hard and it's very complicated. It takes a lot of time to implement. They use tangent linear models, adjoints, ensembles. Ensembles meaning, like, say you have to compute like 50 solutions to these types of equations. And that's, one is a lot, and as is for like these big ocean models or atmospheric models. So the nice thing about this method is you're basically evolving the same system, but you've just added on terms. So you basically added nothing computationally. Your main computational expense is going to come due to reading in data sets and doing the interpolation. So that's really neat. And so what is this IH operator that we use analytically? Well, basically, what we're going to use for our purposes for nice Dirichlet periodic boundary conditions between Navier-Stokes, we're going to use an IH operator that satisfies this quasi-mean value theorem stuff. You can find this in general finite element approximation textbooks. Yeah.
Could you go back one slide? Is it okay?
Yeah.
So I understand.
Mhm.
So IH of V is a function defined everywhere, right?
Yes.
So I interpolating V on everywhere.
As is IH of U now. Yes. Because we're observing U.
Okay, but so in reality, this is something we would be evolving in a discretized sense.
On like a computer,
But
yes.
you could say we're going to be evolving it on a finer grid, and then we're forcing it based on the interpolation of the grid.
Yes, yes, you can think about it like that in the numerical sense.
Okay.
Yes, in computational sense, yes.
Okay.
Yes, 100%. So that's what we did for the impasse model. Yes.
Essentially being interrupted, can I ask a little bit more about it? So are you,
Yeah.
are you imagining that you're constantly measuring flow?
Yes, and there's theory, there's work on that as well. Where,
So V is a function of time.
yes. Yes, so this is assuming that we're observing data continuously in time, which is a big assumption sometimes. And we'll talk about how that can be relaxed.
And you're assuming you've got enough data, so they just interpolated the data as a sufficient constraint on the system.
Yes, yes.
You don't have to use any sort of covariance, so on spread information, which is, I'm going to say, surely this sort of method has been used a lot in the past, but there's still, there has never been enough observations to just interpolate, spread things, have explicit nudging methods, which aren't like what you're talking about. You're also saying interpolating to the observations is enough, which wouldn't be true, never would have been true in our case.
Right, so you have to be careful with that because sparsity is important, right? So what ends up coming into play analytically is there's this interplay between mu and h. So if mu is big, h has to be small. And in fact, mu has to be sufficiently big and h has to be sufficiently small in order for the theory to work.
Yeah.
So yeah. So that is important, and that is why we need to have the discussion and why we're working on looking at the comparisons and applying these to bigger, more significant models because of this issue. However, there is some work by myself and by the crew at King Abdullah University who work on WRF, who have looked at spectral and grid nudging and compared it to this version. And one of the differences from nudging specifically, or nudging was like the first data assimilation method looked at in the 1970s, was that you kind of are looking at V minus U at specific grid points, and you're only looking at them at those grid points. What this does is it's kind of spreading the information throughout the field. However, this is also done, of course, because computationally, it doesn't make sense to just look at the points, right? You kind of want to spread it all throughout as well. And that's the work of Stauffer and Seaman in 1990. And from what I understood from that article, what I compared it to is that generally we're interpolating IH of U, or not interpolating IH of V on the observation grid. And basically what happens there, if you know what edging is, basically what happens is I have a mismatch then. So basically I'd be looking at mu times V minus IH of U. And so if I'm looking at that computationally, that introduces new error. Now that's could be minor, that could be important. We end up showing that it is relatively important in some of our work in our 2021 preprint on the NPAS model with the ocean modeling. So,
We've always had to work out what we call the innovation properly. I think what you want those innovations. That consistency is very important.
yes,
Because we can never just rely on interpolation to spread the information, we have to use covariance measures.
yes, because then you have data error, right?
Some, because that's the only way we can work if we don't have enough data.
Yeah,
And then we use Kalman gain matrix, even though it's only properly justified for a linear case. What it's really doing in practice is to say you're believing your more accurate source of information. And that still works pretty well in a non-linear system. You're always going to believe your most accurate piece of information, so you shouldn't just discard it.
oh yeah, no, absolutely.
It's absolutely, once you go beyond this interpolation, you're going to find you'll need that.
Yes, yes, so that's really important, and we're actually doing a combined mini symposium at SIAM in a couple of weeks to talk about these comparisons and talk about the different perspectives, right? Because from here, we're coming from the continuous perspective. So now we're trying to talk across, because there are really, as you mentioned, there are really important aspects of Kalman gain matrices that we need to understand in comparison to this. Now, Kalman in the linear case lines up with this pretty much identically if you're looking at no noise, right? Yeah, so that's kind of important, but this is nice analytically to start with, and we want to look at the robustness of this and see if maybe sometimes in other cases, like in the lab and experiments and stuff, maybe this would be a more amenable to using data assimilation for experiments in the lab and things like that. And also it gives us some ideas on how to approach a quasi more tractable problem in some sense, I think. That's kind of where we're going from. Yeah. So the interpolate, I'm not as concerned to go into too deeply, but we're mostly going to focus on Fourier truncation because a lot of the analysis is very easy there. So we're going to truncate onto the first n modes. Now, what makes a lot of this work is that basically we have a finite number of determining modes, so and nodes. So that's why the physical points, there's a certain number of physical points that determine the entire flow. There's a certain number of Fourier modes that determine the entire flow for large enough time. So we're going to focus on interpolance, a linear interpolance specifically, so that we can just do IH of U minus V rather than IH of U minus IH of V, and that'll give us some simplicity. Fourier truncation will also give us some insight as well into what we can, how we can analyze this in the context of parameter recovery as well. So, of course, we're going to look at the 2D incompressible Navier-Stokes equation. So just to make everything concrete, here's our standard 2D NSE, and then here's the 2D NSE with, I should say, AOT changes here. So we have minus mu IH of V minus U. So you can think about this as if all this other stuff was gone, this is quasi exponential decay, right? So this is kind of linear in some sense in V minus U. So you have dV dt equals minus mu IH of V. And in fact, you can show that for sufficient small h as long as your observations are close enough together and as long as you're driving it hard enough, i.e. you can find a big mu such that the L2 norm goes to 0 exponentially as t goes to infinity, and the H1 norms goes to 0 exponentially as t goes to infinity once you're close enough to the attractor. So that was the result of Azouani-Olson-Titi in 2014, and that has, so I kind of want to go here. Oh, this one worked. We don't even have to use together. Okay, so this is a stream function plot of Navier-Stokes with a high Grashof number and a nice low viscosity. And basically, we're going to look at the reference solution. So this is what the reference solution looks like. So this would be our U that we're going to sample from. So I'm going to take this stream field, and I'm going to sample it constant piecewise in time. So I'm only going to use 49 measurements of this field, just 7 by 7, and it's piecewise constant interpolated. And I'm going to assimilate this into the AOT edited equation, basically. So, right, so this is the approximating solution. So it starts with some with nothing, and then we just start driving it towards a solution immediately. So that's what's happening here, and we're gonna, I can't skip it because it's in talk, so we'll let it play out here for a second. Yes, so as you can see, it's already starting to capture some of the form of the original solution directly just by the straight up simulation. This part, I don't know why they have a slow motion here. So this is courtesy of Gesho. It was for he did some computational work on this for his master's thesis 2013. Even though the paper came out 2014, that's when they were working on it. So there's some concurrent papers there. And then this one's a little bit, makes things a little more clear. So it shows you that eventually you start, it looks well mixed in fast motion. The important one is going to be the comparison next. Here we go. Okay. So here on the top left, we have the exact solution that we're sampling from. So these are observations, as I mentioned, continuously in time. We're feeding that into the V equation. So that's this equation here. And then this is just the error of these two guys, the scale error. So we're just plotting that here directly. And when it goes black, that means we reach machine precision. And we'll see it already spots are going black quite quickly. And then the whole thing will go black, meaning we've converged exactly up to machine precision, which is really neat. So there's a ton of published works, and I used to have all of them when I started working on this near the beginning of my PhD. And now I've kind of cut it down to what are the most important, because there's now we'll have like 3 slides of papers. So I basically want to focus on the important thing, as you mentioned, is how robust is this in a more realistic settings? How can we take this beautiful idealization in continuous time and generalize it? So we want to look at what happens if we have noisy data when we're converging. How does that, what error does it converge up to? It turns out it converges exponentially still up to an error dependent upon the trace of the covariance matrix times mu. So it's relatively large. There are similar results, I believe, and don't ask Al, I can find the papers afterwards if you want to look at them for Kalman filter as well, and the ergodic cases as well. Another important thing is you mentioned the discrete and time data. So it turns out as long as you're sampling often enough, you'll still get exact convergence to the true solution as time exponentially in time, which is very nice, but they do have to be close enough together. It's not too terrible though. And we can show this as well computationally that it's not too bad in these idealized cases. Another cool thing is, what if we have a model that's incorrect? And so this is a nice test case. I really like it because in these big models like ocean models and atmospheric models, you can do primitive equations and all that stuff, but you're going to lose some of the important aspects because your global grid is too coarse, and we can't refine it enough in order to get the convergence. In order to model the true equation. So we have to parameterize basically what's happening at the subgrid scales. And so what's happening here is looking at the Navier-Stokes Boyd alpha equation. You can show convergence up to an error dependent on alpha if you're assimilating physical data from true 2D Navier-Stokes. So that's work of Larry Pei 2018. There's also been some work on the convergence of the Luray-Hoff-Weak solutions to 3D Navier-Stokes, 3D primitive equations, which is important for the WRF and MPAS work, and then 3D a system assimilating 2D data is also really important. So this kind of gets the point with sparsity. If you're just measuring, if you're looking at, say, the ocean, it's really hard to measure enough data deep enough. So like, what does it mean if I have enough data on the surface? Will that help me recover solutions to the system? The answer is yes.
You have a hand up in the chat.
Huh?
There's a hand up in the chat.
Oh.
Yes, okay, that's me. Hi, Lorette. So I just want to get back to the just the overall, the big picture. The
Yes.
purpose of this is not, or is, to simulate faster, or what is the overall thing that you hope to gain?
The overall thing that we hope to gain is if we don't know the true initial condition, can we recover the solution? And so if we go back to right here, we have the solution du dt, so I'll use the mouse. So the solution to this guy, the du dt equals f of u, we don't know what it is, we can only sample it, right? So we know how it behaves physically, but we don't know the initial condition.
Ah, you know its rule, you know the
You know
F,
it's a rule, but you don't know
know.
where it's starting from.
So now you're going to start with any old initial condition,
Yes, and I'm sorry, I'm usually really good about remembering saying that. That's what's actually so brilliant about this.
No,
is that-
I'm sure you probably did say it. I'm just trying to, from as an outsider to try and get it. Okay, you're going to start from
Yes.
any old initial condition,
Yes,
and
any
okay,
initial condition.
but let's see. I'm sorry. The idea is, in real life, you're not getting U by simulation, I suppose,
Right.
because
Right.
otherwise you'd know its initial condition. You know it from the observations,
Yes, correct,
but the V you're getting by simulation.
correct.
Okay, I see. Okay, and so now you can just use the U that you're seeing.
Yes,
I see. And since you know how it's evolving because you know the F, you can then, oh, okay, hold on. But okay, in the best case though, I'm sorry, I'm still confused. In the best case, you're going to match U.
Right. Can we,
But-
first of all, can you keep this to the end, please?
Okay, okay,
Like, please.
all right.
okay.
Okay, so these questions are all good. Thank you. Thank you all for these questions. So we will focus on some applications here as well. So another important thing is these have been done for a lot of dissipative equations. The dissipative equations are what's really important because that's where you have this concept of finite determining modes and nodes. That's what drives the entire thing. So you can show this, and it has been shown for a variety of equations. Bernard, Buzanaz, a whole bunch of things. Reduced order models as well. It's also been looked at in the context of if we're discretizing, what kind of convergence do we get? Finite element versions. And also one of the most recent ones that I found really fascinating is data given on a subdomain. So if we only observing data on a subdomain, how much of it are we observing? How much of the domain do we have to observe in order to still get convergence? So in some sense, you're saying I only have domain to say data on a piece of the domain. How large does that piece have to be? And can we move that piece, which is useful. So that's some work. Also by Biswas, Bradley, and Jolly, Biswas, Bradshaw, and Jolly analytically, and it's also been some work by, and I didn't add this on here, Larios and Victor as well, who look at moving observers. If I'm, instead of observing at one specific point for all time, say I put a buoy in the ocean and it's moving around. So that basically gives us a sample moving, and what it tells us is that it's robust even to this movement, which is really great news. So specifically what we started working on a few years ago was, what if we don't know the viscosity? So what if our parameter is incorrect? And this is useful because sometimes in these big simulations, you have to say, okay, I have to ramp up the viscosity because otherwise nothing's going to work. So it would be nice if we could take that down. If we have these big viscosities, what does that look like? Can we actually recover our viscosity? If we went back to a nicer case, what does that look like? All that good stuff. So I'm going to take the original system and it's going to evolve. We're just going to be able to sample U from this. We don't know U naught and we don't know nu one. And then we're going to assimilate IH of U into the new system where we have picked a nu 2 of some sort and we picked an initial condition of some sort. Again, the initial condition is not going to matter. And so one can follow the same analysis as AOT 2014 to show that in the limb soup, the air is going to be bounded above by the air and the viscosities, but you're still going to get the exponential decay. And that'll be same in L2 and H1, most explicitly, which is pretty neat.
Okay,
Yes,
you're going kind of fast.
sorry.
What you're saying?
So basically, remember how before we said U minus V converges exponentially to 0 if the viscosities are the same? The viscosities are different now. So when you do the analysis and you work through the energy estimates, you're not going to, this, if nu 1 equals nu 2, this is 0 and you recover the original convergence. Now, since nu 2 and nu 1 are not the same, your solutions are not going to line up. And in fact, they're going to obey this. They're going to obey this bound.
So the idea is that you don't know the exact, you've got an error in your viscosity.
Yes, yes.
But I mean, if you could observe exactly, okay,
Mhm.
then one observation in time should be enough because you're only recovering one parameter.
I haven't thought about that too explicitly.
You want to recover one number. The viscosity is constant here, correct?
Yes.
Okay. So I think one observation in time should be enough.
But
Yeah,
But
sure.
yes,
but that's if you had an exact
I
observation.
understand. That's what I said.
Oh, okay.
Okay.
Yeah.
Yeah.
So I guess that, yeah.
You'd also have to know the time derivative exactly as well, right?
It's true.
So
Well,
that could be
not
tricky.
necessarily, right? I mean, use controllability to get that value, but the point is that have you thought of, whether you can recover the viscosity beyond its of 5 fields or so? Because even with error, you shouldn't have to observe for all times. Say.
I see. Interesting. I haven't thought about that explicitly in that context. We maybe have thought about it a little bit in the context of Lorenz, a tiny bit.
Okay.
And I'll talk about that in a bit if we get to it, which
Yeah.
we should. But the point here is, as Adam was saying, we might have all these other problems cropping up. So what is the error here? What's happening explicitly in the standard theory? And can we somehow, and the cool thing about this is that when we look at this computationally, if we're taking our turbulent to be the interpolation under finite modes, we're going to get this graphic. And what happens here is the IH of u minus v, if you go back to the bound we chose, is going to be bounded above by this h. If you look at IH of u minus v in the L2 norm, it's bounded above by this. So therefore, it also obeys this bound. But IH of u minus v might be 0, and this might be non-zero. So that's problematic. So computationally, it helped us back it up that the bound is this bound here. So the red line is plotting this with a constant of like 4 or 5. And then we're plotting the IH-L2 error here. So if we're changing our viscosity nu2 that we're guessing, we can see that the IH error is pretty much tracking the bound that we actually did. So it actually kind of shows some sort of sharpness of that bound, at least in terms of the characterization of nu1 minus nu2. The C constant obviously is going to be massive from the standard analysis. So the question here is, though, can we recover the true viscosity? And we'll want to do that computationally, even in the presence of other errors. So what happens here is that we're going to look at the heuristic for recovering the true viscosity. And so we're going to take the difference of the two equations, the Navier-Stokes from the data assimilation equation. And when we do that, we're going to get our mixed terms here. We're going to get AV. So then our
W is u minus v.
thank you. W is u minus v. So W is our error. So I'm looking at the error equation now. How that's evolving. So I'm going to apply IH to both sides because I have, in real life, I only have IH of u. I don't have u. So if I apply IH of u to both sides and assume lots of things commute, this is a heuristic, then what happens here is I just do some inner products and I'm going to get these 4 terms. I'm going to get a time derivative of IHW and L2 squared, and I'm going to get nu1 minus nu2 IH of AV, IH of W inner product, and then I'm going to get a square term weighted by mu, and then I'm going to get a nasty square term. So IH of AW minus BWE minus BUW inner product of IHW. So notice this term here is like order W squared in L2 norm. This term is order W squared in L2 norm, but it's weighted by this massive mu. This guy here is only order W, and this one's a time derivative of W squared. So if I'm just doing a magnitude analysis, I really want this last term to go away, which is great because IH of BWV, who knows what that is. So these 2 terms are really important. So this term we can argue will go away. This term we can also argue will go away looking at the computations here. So if we're actually running this, so here's a bunch of nu2 guesses near nu1. Nu1 is chosen to be 10 to the minus 3. So these are all numbers around 10 to the minus 3. So basically I'm going to run the simulations with these incorrect viscosities and I'm going to plot the L2 error. And what happens is I get the L2 error of IHW. So I'm going to plot it. It's going to decay exponentially up to some value. And then it's going to plateau. So if it plateaus here, that means it means basically in time that the time derivative shouldn't be changing. The error of the time, the error of IH of W L2 norm shouldn't be changing in time. So then I can neglect it. And we can see here, this is just a double check us. This here is mu IHW squared. This is the nasty W squared term. Order of magnitudes are much lower. So it just justifies our magnitude analysis that we just argued out loud. So we can ignore both of these terms. And now what's left are 2 terms that are one, computable in a real world setting and easy to write down. And we can actually write down a recovery formula for nu1. So that's very simple. Just divide by IH of AV, IH of W, and then add nu2 to both sides. Done. So this is really interesting. We wanted to see, okay, so let's think about implementing this directly. If I implement it directly, I'm going to start with my incorrect viscosity. I'm going to run the simulation. So I'm going to get the exponential decay until the error flattens out, right? So it's basically, I want to get to the point where I can neglect that time derivative of the error. Then I'm going to go to my V equation and I'm going to update the viscosity. And then I'm going to run it again. So then I get what happens here. this is the dark blue line. So there's two algorithms here. We're going to focus on the blue one. The blue one's the one we just described. So this blue line here is what happens to the error. So here we have the error decays and then levels off. And then at the sharp point is where we change the viscosity. So then we're going to get the exponential decay, and then it's going to stop. And then we're going to update the viscosity again, all the way down to machine precision. Not only do we recover the true solution, we also recover the true viscosity because we're actually updating the viscosity explicitly. So this is a nice computational live simulation that allows us to recover the viscosity explicitly. We're hoping this to be robust in a bunch of different scenarios, which computation we show for Lorenz is. Yes, so this was published a while ago. The orange line, I won't go into that too much. That's for an integral formulation, because what if your time derivative looks like it's flat, but maybe you could get something like this. So if we integrate that out, it should be fine. And then we see that it does the same thing. In fact, we see something slightly better in some sense. So here we've struggled with the proof for this for quite a while, because you have this thing you're dividing by, which is this IH of AV, and in product of the IH of W. How do you know what you're not dividing by 0? How do you control the time derivative of IH of W? What does that even look like? Oof. So instead, after a while, we ended up going back to a simpler case. This is where we actually go back to nudging, because nudging is where we're basically nudging at all point at a specific point in space now. So IH of W, remember, is of course interpolation in space. Lorenz is time derivative of x, y, z. So we're not actually going to have any interpolation on x. We're not going to have any interpolation on x tilde minus x. So Lorenz equations, of course, would just be x dot equals sigma y minus x, y dot equals rho x minus y minus xz, z dot equals xy minus beta z. So then the assimilation equations are just going to add on our feedback control terms, minus mu1 x tilde minus x, mu2 y tilde minus y, and mu3 z tilde minus z. So z tilde solves the data assimilation equations, and z solves the original Lorenz equations. Okay, so our recovery algorithms, we're going to derive them in the same way as we did for Navier-Stokes. And I've had some confusion on this in the past because I thought the other one was sufficient. So we'll just run through it really quickly again. If we're taking u to be the difference in x tilde minus x, v to be the difference in y tilde minus y, and delta sigma to be sigma tilde minus sigma, if our sigma is incorrect, our Prandtl number, then we're going to similarly multiply by u. Right, we're not taking inner product anymore, we're just multiplying. And so then when we do that, we're again going to get terms. So this is what it turned out to be. I'm going to align my time derivative and my error squared terms over here. And then my linear and error plus my mu u squared term, because mu again is supposed to be large. So again, I can neglect these and just focus on these. And so by magnitude analysis, that's much smaller than that. So to leading order, we should have something like this. So it's the same idea. And you can do that for rho and for beta as well. So what that shows us actually is not only, we wanted to not look at this, of course, in just the setting of recovering viscosity. What about we're looking at the Boussinesq equations? What if we want to recover the viscosity for the and the thermal diffusivity? What if we want to recover both of those? So this is also another insight into multi-parameter recovery. So here, what this shows is if we assume that we're not dividing by 0, which we can argue computationally, it looks like the set at which these are equal to each other is of measure 0. We do have to figure out how to prove that at some point, because inverse problems are ill-posed in general. So if we assume that we have a large enough mu, then we can show that what happens is that the error decays algebraically. So you can show it by an induction proof, and we'll walk through that very briefly. So the important thing here that we missed for a while is that we were assuming we wanted to keep nice low regularity on things to see if we could still get the proof, because clearly it worked for all these nice things and computationally. But the key thing that we found going back to Lorenz was we needed estimates on the time derivative. So we have to look at not only the original system and bound its energy, we also have to look at the time derivative system and bound its energy. And it turns out that you can just use a bunch like pages of energy estimates to show that you'll get exponential decay plus, again, this delta sigma squared argument. Now, the cool thing is we can run this whole thing again with delta sigma, delta rho, and delta beta all at the same time, and everything will hold. So not only is this going to show parameter recovery for one parameter, but it's going to show parameter recovery simultaneously for all parameters. So these are my two bounds that I absolutely need. There's similar bounds, and of course, on the attractor and things like that that we'll need to use as well directly in order to control things. But these are the two key players: a bound on the energy for the original system and on the time derivative system. So if we rearrange our sigma recovery equation, sorry, not even the sigma recovery equation, if we rearrange the U dot equation, right? So my delta sigma only appears here. So I know that I can write delta sigma explicitly in terms of the equation, right? So that's where I need to control this U dot term. So that's where the energy bound on time derivative comes into play. And then of course, this is where the energy bound on the regular system comes into play as well. So if I substitute in, so say I'm sigma n, I'm using my nth sigma, right? My first guess, for example, if n is 1, then I can say, okay, so here delta sigma would be sigma 1 minus sigma. Substitute that in, so I can substitute this in directly into the parameter recovery algorithm. So now I have something exact. And so then I can look at sigma n plus 1 with our update minus sigma, and then I'll have to control this directly. So here I'll need the time derivative estimates. Here I'll need the direct estimates on V and U. And so assuming the lower bound on that y delta, y tilde minus x tilde, right, that we're dividing by, we have to assume we're not dividing by 0, plus those energy bounds, we can get that sigma n plus 1 minus sigma is less than or equal to epsilon prime sigma n minus sigma. Now, this epsilon prime is controlled specifically by the choice of mu. So if I go back to this, you'll notice that not only do we have exponential decay, but because we're bounding it, before you do Gronwall, before you're bounding it, you're going to get mu over 2 times stuff involving k plus a constant. So this over 1 over mu is coming from doing the Gronwall estimate, which is really nice because you're integrating that exponential against a constant. So that's really helpful, and that's key, actually. That's really key. So that gives us the epsilon control here. So that allows us to make this small, but it requires mu to be large. So thus we have algebraic monotonic convergence of the parameters. This is true for sigma, beta, rho, and beta all simultaneously. Of course, that's not necessary to do if you have the specific. So I specifically want to focus on if I have the x equation, I can solve for sigma. If I have the y equation, I can solve for rho. If I have the z equation, I can solve for beta. And I can do combinations thereof. If I have all three parameters incorrect, but I know all the data, that's what I should clarify. If I know all the data here, if I know all of the data, if I read this, right, this is continuous in time. So if I'm assimilating X, Y, and Z, I literally know all the data and I don't have to do all this work. But if I don't know all the data, say here, and I just know the true beta, I can recover rho and sigma directly. So I don't have to know everything. If I just know X and Y, I can use this method to recover sigma and rho. So that's really interesting. And it's especially interesting once we look at it computationally and we start adding on error, like Gaussian error and things like this. And what about sparse in time? How do things work as well? And so before I go into that, though, I would like to mention that this approach, now that we know that we need to have bounds on the time derivatives, if we're specifically taking IH to be the Fourier projection onto low modes, it is a 22-page paper of a lot of energy estimates, brilliantly done by Vincent Martinez, our co-author, who also worked with us on this paper. This is, I guess I should say here, is Carlson, Hudson, Larios, Martinez, me, and Whitehead. 21, this just got accepted in the DCDS. So based on all this work, Martinez just published in nonlinearity, the proof for the parameter recovery for the 2D Navier-Stokes using the interpolation using the interpolant of Fourier projection. However, he does remark that he thinks he can, it's generalizable, but extremely technical, although it was already extremely technical, to do it for more general interpolants, which is interesting.
Question?
Yes.
So the assumption that X is not equal to Y
Yes.
is, of course, not true. You pass through that surface all the time.
Right. So,
but of course, if you could just imagine, well, let's just take a few more time steps and
exactly. So that's kind of
my
the assumption
question
here.
is,
Yeah.
Is there an analogous assumption that Vince is making for Navier-Stokes?
Yes. Yes, there is.
How egregious is the assumption?
I don't believe it's that egregious, but he doesn't remark on it super much. I have to review that again, but
Okay.
yeah, that's something we're still looking into because there's actually this is quite an assumption in some sense, but as you're saying, pointing out that if we take it at specific times, we're using left-hand arguments, like we're coming at it from the left hand in time, blah, blah, blah. There's a bunch of
But
technicalities
in
there.
practice, if it's violated, you could just take a few more time steps before you go back to your parameter.
Exactly.
I see.
That's exactly what we do. So we actually enforce that condition directly.
Even this is just the inner product, it doesn't want to be zero. It's
Yeah,
gonna be with the page.
yeah, it doesn't want to be zero, but I don't remember all of the reasons
In
behind it.
practice, you just,
Yeah, you just
if it's that, you go to it.
Okay, got it.
Wait a second.
Yeah, exactly. So moving on from here, this is some computations with parameter recovery observations every so many time steps. We'll show that we can recover this is the error and so this is your delta sigma. If our sigma is incorrect, we recover not only solution, but also the parameter. Similarly for delta rho, delta beta, delta rho, delta sigma, delta beta, delta sigma, delta rho, and then of course all three, which that's a trivial case regardless. Yes, and then we had the momentary, the reason for the block there is there's momentary convergence to an exact value at that time. So that's just some sort of course, noise at some point. Yes, okay. And then Adam, you're free to jump in here because you know this part a lot better than I do. Parameter recovery as well with sparse observations again. That's what we're going to see in real life, but we're also going to see errors in our observations. So we add on some noise with an amplitude of eta, and we still get error up to, as expected, the error determined by the noise amplitude here. But some of the significant things here that we have to worry about, and in both cases, is that with sparse time, and we're not sure why yet. I have thoughts though, and we have numerical thoughts as well as to why this is the case. Mu has to be different for the parameter recovery when we're taking sparse observations, as compared to the mu we're actually using for the data assimilation specifically. It has something to do with, my guess is the delta t. It is different for the stimulation versus the parameter recovery. And so that affects the choice of mu, because the mu in practice is much smaller than the mu in the theory. Yes, okay, I think that's most of the, okay, cool. That is most of the parameter recovery stuff. And I do have some extra time. Okay, excellent. Are there any further questions on the parameter recovery before I move into a different section?
What's
Yes.
the IoT stand for?
Azouani-Olson-Titi. So you'll see in the literature, it'll be either AOT or CDA, where CDA stands for continuous data assimilation, but that can be problematic sometimes because CDA is also used to describe a class of continuous data assimilation algorithms, specifically nudging and this method. So Azouani-Olson-Titi comes from the original paper where this method was proposed. Yeah, in 2014. Yes.
So what is that method called?
AOT algorithm, or that's not for the parameter recovery, that's just for the data assimilation in general. Parameter recovery, we just call it parameter recovery, or Josh's algorithm, or Benjamin's algorithm, because there's another algorithm I'm not discussing in here because it's not something I remember yet.
I see it takes inspiration from multi-fidelity methods like co-creating.
Say that again?
I see that it takes inspiration from multi-fidelity methods. When you wrote the very first equation, dv by dt equal to f of p minus mu of I of p minus mu, that's the right hand side is exactly of the form of what we do in co-creating methods.
Okay. Yeah, that'd be cool to talk about a little bit more later, because of course this is very similar to a lot of different methods and a lot of different approaches. Yeah.
Thank you.
Yeah, for sure. Okay, so with that, we've got about 15 minutes to move on to a few other things. So specifically, we were originally looking at this. We were thinking that it could be causing problems if we just change the viscosity numerically. We ended up arguing ourselves out of that, but it still led to a nice paper. Specifically, what happens to the, we want to analyze the sensitivity of solutions to viscosity. And we combed the literature and discovered that it had been shown for the formal sensitivity equations, the existence and uniqueness had been shown, but not that it was satisfied specifically by the Fr&eacute derivative of U with respect to the viscosity. So specifically, we want to say, okay, let's actually, instead of using standard Galerkin methods where something converges to this system of formal sensitivity equations, can we actually construct this using the difference quotients. So our instead of looking at a Galerkin like sequence, we're looking at a specific sequence of difference quotients. So the formal sensitivity equations, of course, is you just take d nu and you slap it on Navier-Stokes, correct? So I would take Navier-Stokes, u is going to be du, u tilde is going to be du d nu, p tilde is going to be dp d nu, v tilde, because why not do it for AOT as well? That was the original motivating factor anyways, v d nu, and then q tilde is our pressure here would be dq d nu. So if I take that derivative with respect to viscosity and I apply it to Navier-Stokes and apply it to the AOT system, I obtain these mixed terms. So I'll get u tilde sub t plus u tilde dot grad u dot grad u tilde, and then minus nu Laplacian u tilde. And then of course, because there's a nu here, we're going to get an extra Laplacian on u. And then similarly, we're going to have the exact same thing for AOT plus whatever comes out from the interpolation term here. So these are the formally stated, right? They're not explicitly stated.
Can I ask a question
Yes.
related to the pressure?
Yes.
Pressure is a kinematic constraint, it's not a dynamic constraint, so you are covered from the equation. So if I differentiate the equation with respect to nu, I'm gonna get the difference. So what I'm trying to say is that, is it clear that the ddu is the Lagrange multiplier, the gradient of the ddu is the Lagrange multiplier? I presume, I mean, you still divergence, you twiddle, I mean, still divergence.
Yeah, u is still divergence free. So when we're doing the analysis, we basically drop that term, it's in there for posterity.
Yeah, but what I'm trying to say, I think that p tilde should be determined from the divergence free constraint, not simply by taking the derivative. I mean, really, you get exactly the same thing, but is it clear?
Yeah. And
I'm not really sure. Thought about that.
this is like a thermal. When you subtract the two equations.
Okay.
There might be more details there. I would love to ask you more about that later, but since we don't generally worry about it, we just project it out and do the analysis in the divergence-free space.
Okay, so you're not trying to recover, I see, you're not trying to recover the pressure sensitivity.
No,
Okay,
no, not at all,
okay,
not at
okay.
all. Yes, not at all. So we're just looking at these in like the formal sense,
But
then, yes,
sorry, Anna. Hi, Elizabeth. This is
Hi.
Idris.
hi.
Anna, I don't understand your question. I mean, formally, you can differentiate the equation with respect to nu, and you get.
No, yes, I was just wondering, maybe it's obvious. I mean, it's just that I would have just recovered. I mean, maybe you get.
Think about the pressure as the nonlinear term. So you should object equally to the derivative of the nonlinear term, u tilde dot grad u plus u dot grad u tilde. The same thing. So the gradient of p tilde is of the same sort.
But okay. Okay, fine.
Okay. Sounds good. All right, so then we're going to look at the difference quotient with respect to viscosity. So instead of, we don't want to just prove that solutions to this in the divergence free space exist. We want to prove that we can recover them from some limit of difference quotients. So we get some sort of derivatives actually satisfying these equations. Turned out in the literature that hadn't existed yet. There's a ton of work for linear theory and for some more general equations using some semi-group theory. But it was not specifically for these types of equations where they specifically have this nonlinearity. So instead we looked at, let's just take the difference of, so if we're looking at a difference quotient, we're going to look at Navier-Stokes with one viscosity and Navier-Stokes with another viscosity. And we're going to subtract them and we're going to send nu2, for example, to nu1. Oh, looking at NSC directly. So D here represents U minus U2. U has viscosity nu, U2 solves NSC with viscosity nu2. So this is your difference quotient directly. So your P comes here, P minus P2, nu minus nu2. So then we're going to take this guy, we're going to consider this guy projected into divergence free space. We're going to do the same thing with the AOT system, identically analogous. And then our theorem is that we can say that there's a subsequence of these difference quotients that converges to a unique weak solution for Navier-Stokes by using, of course, uniform bounds in nu k. So k is what we're indexing our nu k sequence by as we're sending nu k to nu. And we're going to get those uniform bounds in K. We're going to send U to K to U and L2 0 to V. We'll get those uniform bounds in K on the difference quotient as well. So we'll get the weak star convergence in our usual L infinity AH space, and H being, and I guess I should clarify, H here is the completion of C infinity periodic mean free in L2, and V is the same thing completed in H1. So that's standard notation in some literature, but not everybody is used to that. So L infinity H, L2 V, we'll get uniform bounds on the time derivative in L2 V star, and then Navier-Stokes compactness theorem will give us the full convergence in L2 V. So L2 H. So then we show also that this D coincides with the Fr&-eacute derivative in L2 H. To actually get it in the Lorenz space takes a little bit more work. And we may have to actually require a follow-up paper and kind of a backdoor method that we think may be available via some work by John Singler in 2008. But that's actually going to take an entirely different approach and requires a slightly different proof. But I think it's amenable. Similarly, we want to do the same thing for strong solutions. It's identical. Similarly, for the formal sensitivity equations for the AOT system, we'll also get direct convergence in L2V as well for the strong solutions. But the important thing here is, oh, and I didn't put it on this slide. Depends on which program I do it in, which PDF I was using. But we also showed this for the Euler limit as well. If we're using the work of Mahmoudi, where we have initial data in s greater than 2, we can also show that the derivative with respect to, like, if you set nu equal to 0 and you send the nu case to 0, you'll get the convergence as well in the usual sense following Mahmoudi's work. Yeah.
I think I'm lost.
Okay.
What does this have to do with anything else you were talking about, and why do we care about this in relation to the previous parts of the chart?
So originally what we were thinking when we were originally doing it is, okay, what happens if we are looking at it computationally? We're changing this viscosity when we're doing this update. Is that going to cause some sort of, is the system going to freak out if we do that? Is it going to cause some instabilities? How sensitive is the system to these changes in viscosity? How is it going to be affected by that? We argued out of that eventually that we didn't need to worry about that because of how nice Navier-Stokes is, but basically that led us into looking at this directly. So we were looking at, okay, formal sensitivity equations, we can show that they're bounded and they're nice and everything's well posed, but we don't know that it's actually the derivative with respect to viscosity. We know heuristically it is, but we wanted to show it rigorously. Yeah.
In the interest of time, I suggest we take this as a assignment.
Yes, okay.
I think we're actually out of time almost.
Almost, we got about 7 minutes left. Yeah.
Go for it.
You're right. It's orthogonal to
It's kind of orthogonal to it, yes.
Sorry?
Okay,
May I add a comment here
yes,
about the viscosity thing? Can you go back?
yeah,
Unfortunately, I know that paper has been published, etc., and beautiful and nice, but the news is that this result is very well known from a long time ago. In fact, when you look to the complexified Navier-Stokes, and you can complexify the time, and you show that the solution is complex analytic or real analytic with respect to the time variable. The same technique, the same work, you can think about complexifying the viscosity. Well, it sounds crazy, but that's what mathematics is about. You can think about the viscosity to be a complex number with the real part positive. Then you can show that the solution of the Navier-Stokes strong solution is complex or is analytic function with respect to nu. Not only has the Fr&-eacute derivative the way basically it's done, the proofs are not much different than these, but it is done at the level of Galerkin to show that u as function of a nu and t as a new complex number and t is a complex number are complex analytic function in the real part of t positive, real part of nu is positive. Now, I think this result is due to Foyash long time ago, like sometime from the 70s, okay? So this is in some sense consistent with your result, but the result is even stronger there that it is complex analytic or real analytic function when nu is positive. This is just a comment on the side.
yeah, no, I'd like to discuss that more with you later. Yeah, that would be great, because the most recent work we found on this was a thesis And they were just showing the existence using Galerkin methods to the formal equations directly. So that was the latest result I found, but yeah, I'd love to hear more about that.
Literature.
Yeah,
This is interesting. Okay.
yeah. That's really interesting.
It's the same proof that basically Foyash gave. He complexified time and viscosity, but they emphasize the time complexity because then they can get estimates on the time derivative by Cauchy-Riemann and by Cauchy formula, and then from there he can get estimates on the Laplacian, which he needed it later. But the estimates on the viscosity was never used in some sense. So now you're finding good application for it, but it's exactly the same proof work.
Okay, very interesting. Yeah, if you can point me to that resource, I would later this week or something. That would be really great. Love to read that. Okay, I think I'm going to skip over the nonlinear algorithm because that's kind of actually a work in progress and we're editing it as well. I've talked about it before. You can find some old talks on that as well. But specifically, since we have a few minutes left, I'll briefly talk about the applications to ocean models. We specifically were looking at global ocean simulations. I mentioned earlier that global ocean simulations can't resolve all these physical processes due to computational expense, so you lose some of these subgrid scale effects. So the largest cities have this length scale, and that is proportional to the Rossby radius deformation. In our setting, basically you have eddies that spin off larger eddies leading to eddies of smaller length scale, and hence you have this classification of different model types, eddy permitting versus eddy resolving. It's extremely vague. There is no formal, no rigorous definition of it, or even formal definition of it that I've seen in the literature. Basically, do we see anything anything below the largest eddies, or do they have any spin-off? Then we have eddy, and then they continue spinning off. So those are kind of eddy resolving. Current fixes for this are like in regions where that matters more. They'll refine the grid so that you can get more of this. If you're hitting boundaries or something, you're going to get more of these spin-offs. So those are variable resolution models, or to recover some of these subgrid scale effects, you are working with parameterizations. So you basically parameterize what's actually happening at the subgrid scales because you can't actually simulate them. So what we wanted to do is see if data simulation would help recover some of those subgrid scale effects based on what it was telling us about the viscosity error. So we can get this convergence up to an error determined by the viscosity error. You can kind of think of, if you change that to the Reynolds number and look at it numerically, you can think of the Reynolds number as relating to those scales of the grids. So we wanted to assimilate these horizontal velocities, temperature, and salinity to the primitive equations, and then we wanted to analyze 4 specific things: eddy kinetic energy, mass transport, diffusivity across these isopycnals, which are basically lines of constant density, and then of course looking at root mean square error, which is their analog of L2 norm. So I don't want to go into the test case too much, but basically what's happening is we're creating this double gyre, they interact, and it creates the eddies that we're looking at. So we're going to look at 2 simulations here, 8 kilometers and 32 kilometers. And 8 kilometers is the high res, 32 kilometers is the low res, so that they're eddy resolving and are eddy permitting. So we're assimilating data from the high res into the low res. And that's what's happening here. So this is the point I really want to focus on, because this is the one I mentioned earlier. Comparison to nudging, the original data simulation method back in the 70s where all this kind of started, is our observations are given on this rectangular grid, but in practice, we're using a lot of these fancy grids. Specifically, MPAS uses this Voronoi tessellation. This is hexagonal grid. And notice that in continuous space, we don't have, we kind of think of it as, oh yeah, well, we can just sample anywhere. When we're looking at these grids, they're not nested, so we can't just sample anywhere. So if we're looking at observations, we want to take the observation grid and interpolate to the computational grid. The model, however, we can't observe on the observational grid. So we can either just stay on the model grid and then just look at IH of U minus V. And then that's, again, the problem with our term. We don't have apples to apples. We have this IH of U minus V. We're going to get errors propagating from that if we're doing the data simulation. But if we interpolate to the observation grid, we would assume that it would be a little bit better, more like it's like IH of V. But because this is sparser than the model grid, it should be a better approximation of the true IH of U minus IH of V. And it turns out that it's 12:15. I won't go over this too much. This is the control. These three are different AOT simulations with different mu's. And then this one here is the control simulation. So these are all low resolution. These three are data simulation, but they match up really well when interpolated on the coarse grid to the fine resolution one, which is really nice. But the important thing here is that if we're looking at nudging versus CDA, we end up seeing these comparisons here. We get this decay. The lines that are smaller with the X's are CDA or AOT, and then the lines with the dots are the error for the nudging specifically. If we're using data on a finer grid, the difference between them isn't so much. But if our observations are on a coarser grid, the differences are actually quite different. In fact, up to 30% improvement in error just using the double interpolation over just no interpolation on V at all. So with that, I will conclude. We're doing a bunch of different things with multiple parameters. I'm also trying to work on a model bias study for the global ocean. That's kind of on the back burner because we're editing this paper. And then also some comparisons to statistical data simulation methods, which we need to talk to Price and Viswas about as well. And then we're also looking at for covering potentially the forcing function. So that's kind of a general overview of some things, but high focus on the parameter recovery. So I hope that's interesting.
Any further question or comment?
So you're trying to force a low resolution model to look like a high resolution model.
More or less, yeah.
But what we really have to do is calibrate a subgrid model, which you then, having made it agree on a particular training case, then we have to agree on other cases.
Yes.
And that's a bit optimistic, I suspect.
Yes.
I mean, essentially, you're doing something where you specify the problem very exactly, and you're trying to simulate real observations into the real ocean in that territory at all. So you're aware of that.
Yes, 100%. So I started this a little more naively and then discovered over time, there's a lot more that's going on here. A lot more of the sparse observations, noisiness. This is a very nice test case, but we have a lot further to go from here.
So here you want to do everything exactly and get very nice results. As soon as you depart that situation, it's a different game.
Yes. So I think, is Colin working with real data right now? So
The student who's at Los Alamos implementing in large scale advanced code right now, does exactly that. It's a working environment.
yeah, so that's Colin Victor, my academic brother. So he took on this for graduated in some sense. Something slightly different, but very similar.
And so, I mean, in the original statement and now in the end, you say something about camera filters, and that if I understand, you basically said that you don't need, I mean, the Kalman filter starts with the idea of optimizing something so as to get a state estimator from as few measurements as possible. Now you are saying, I don't need it because a simple constant feedback is enough if I have H small enough. But aren't these two opposite purposes? I mean, still having as few measurements as possible is a sensible practical purpose. So how far are you from H large enough?
Yes, so the work on that with H large enough, so theoretically, H has to be very small. Computationally, in idealized settings, H can be quite large. Like in the Gesho video I showed you, we only needed 49 of those observations interpolated quite coarsely.
Yeah, but I mean, classically, simple constant feedback was born first. And then people started to optimize a matrix for it.
Yes.
Now we are dispensing with the matrix, but why? I mean, wouldn't it be better to use it and still, you can still do all this with a feedback matrix? Why do you only use a scalar?
Yes, so you can do a lot of this with mathematics when Kalman filter. So you can do the analysis with Kalman filter if the model is linear. But a lot of difficulty that comes in with is analytically, it's very difficult to show things. There's only been a handful of papers that actually show this direct convergence. I think the latest one is only 2016, and I think it's Maida and Kelly, and they're showing it using geometric ergodicity. And I believe that's only for ensemble Kalman filter. So it's been working its way there. And we're actually having a seminar on it in a couple of weeks to discuss more kind of the comparisons here. But the important thing about this as well is not only that, it's not that they're opposed, right? They're sisters in some sense, right? Of course, in fact, in the linear case, they're identical with no noise. You can get the same derivation. And I do want to put that in here at some point. That's actually on my plan to put in my talks as the introduction.
The answer is just that you can't prove convergence.
It's really hard to prove convergence for Kalman filter, and because a lot of what gets knocked out is you make this Gaussian.
Convergence, if you want to build a Kalman filter, but if you just take one and then let H go to 0, it will be the same H.
Say that one more time.
I mean, if you take a given Hilbert matrix
Mm-hmm.
and then let the resolution change, it should be similar.
Can we maybe just,
But okay, doesn't.
no, I'm just saying you will have to
Sure.
continue, but let's thank, people want to say all absolutely, but.
Yes. So another thing here, so I'll have to ask you more about that question, specifically about something H to 0, but the common filter is a lot more expensive to implement. This is cheap to implement as well, computationally. So maybe for like some models, if you want to do a simple simulation, you don't want to do and learn all of common filter, you can just do this. So there's also that advantage as well. So there's trade-offs in both settings. Yes. Yeah.
I mean, this is not a replacement.
No, of course not.
It will be integrated with that.
Absolutely not. Yeah, it's not a replacement, not at all. Hopefully it gives us actually more insight into into things, because Kalman filter analytically is so hard. Hopefully it gives us some insight, and with this parameter recovery stuff, with Kalman filter, you can do some parameter recovery ad hoc, but not necessarily, I haven't seen any analytical work on it at all. And this is like, we already have the analytical for parameter recovery in here, and that's actually really, really cool. So it gives us some more insight potentially by looking at it this way. Yeah.